Okay. So, having looked at linear shift invariance of system and how to characterize system, right, we talked about convolution being an important operator, right. So, this is fine. We are talking about f of x and g of x, which are all in the spatial domain. So, we could use convolution property, right, and we talked about how the system transfer function concept, right, system impulse response point spread function. How do you use the system impulse response function that connects your input and output through the convolution operator? So, clearly that is fine, this is very intuitive, this is straightforward, but there are other ways through which, other operators through which we could still analyze the system properties. So, if you looked at your 1D, if you recall your 1D systems analysis, you will notice that we used to call their time domain analysis or time series. So, you have signal, usually the independent variable being time, right. You will analyze time domain, or you could actually capture the signal in the frequency domain, and so there is an important operator that comes in, important transform that comes in, which is Fourier transform. So, now that we have seen how convolution could be used, right, that connects the system function and your input and output, let us see how we can make use of Fourier transform or the other domain or other equivalent domain to analyze a system. So, this is going to be again a very quick review. Okay. So, you will appreciate that all of the like we saw for the systems review, the Fourier transform is going to be a direct extension from 1D to 2D. Of course, there are a couple of aspects that may look initially little complicated, but once you understand how to read that, right, read the equation in English, make it intuitive, I think it is not going to be that complicated. So, you need to you have to take it at the level of a review material. Okay. So, let us start with Fourier transform, right, Fourier transform, a review. So, what do we mean by that? Oh, so there is a f of x comma y, which is what we have been dealing with so far, right. F of x comma y is your spatial variable in 2 dimensions, that is what we have been working upon. So, now this is called as your forward direction, this is your Fourier transform, and this is your inverse Fourier transform. So, if you really have a careful look at what it is, of course, u and v are the spatial frequencies. So, if you recall at this point of time, before we jump in and interpret, just for you to feel convinced that this is a direct extension, like I said last concept as well, you can do x of x comma y was your t, right, x comma y was your t. So, your u and v are your spatial frequencies, which was say f or 2 pi f would be your omega, right. So, whichever way you are familiar with, you can do that. But if you substitute this, you will quickly realize that f of t e power minus j 2 pi f t dt, only one variable, right, and there will be one integral. Your LHS will be f of j omega or whatever frequency denotation you do. So, it is a straightforward extension. Only thing is the time variable, instead of time variable, now we are going to deal with spatial variables. So, therefore, we already interpreted, visualized these frequencies, right. Go back to the example where we talked about lines, we talked about the pattern, right. It was vertical parallel bars, right, black and white alternate, and then that was at an angle. So, we visualized frequencies. So, now what here you see is how do I break the signal f of x comma y or decompose the signal f of x comma y into its frequency component. So, essentially we did this in time in spatial domain by using the spatial impulse response, right, the direct delta function, your point impulse response, right. We talked about f of xy, you can pick point. So, essentially you can see the arbitrary function f of xy in terms of your impulse response. So, instead of that, now you are breaking or you are decomposing your f of x comma y into complex exponentials. So, that is what is happening here. So, you are breaking f of x comma y in terms of complex exponentials. Again, what is this complex exponential? E power. So, when we covered the important signals, we covered complex exponentials and we wrote that in terms of sine and cosine. So, essentially what you have is, you can see this as sine and cosine with some frequency, which is your spatial frequencies u and v. So, you have writing or decomposing this f of x comma y and seeing how much of frequency content is there. So, your f of u comma v. So, how many frequency content this f of x y is composed of. Okay. So, naturally this is your forward, and similarly if you are given all the frequency composition, then you could get back to your spatial domain f of x comma y. Okay. So, a very simple concept wise direct extension of your time domain, frequency domain to the time in one dimension, right, time domain to frequency domain to time domain, forward Fourier transform, inverse Fourier transform, same thing. Of course, if you do that, then you are representing your signal f of x comma y in terms of its constituent frequencies, and therefore we can write the you have to have the integrals, right, you have to be able to evaluate this, and when is it sufficient, right, you have to have a sufficient condition when you can compute the integral so that you can calculate your Fourier transforms, and that is happening if f of x comma y is continuous, or if it is discontinuous, it is only finite discontinuities, and in any case it has to be absolutely integrable. Only in this case you can calculate the Fourier transform. It turns out that most of the transforms that we will be applying for this imaging systems or signals that are participating in this undergoing this in the medical imaging systems, it is reasonably good approximation. So, it satisfies this. So, most of the time you will not have a problem calculating the Fourier transforms, rather it is the sufficient condition will be met. Okay. So, it is very powerful, as no, I cannot reiterate it enough. If you have done any signal processing with one dimension, you know the powerfulness of your Fourier transform. So, same thing extends here also. In fact, this we will not jump the gun ahead of its time, but then you will notice that understanding of the Fourier transform is very important, or you have to be very comfortable, because in one of the modalities that we will cover, the signal you will be acquiring can be thought of as directly estimating the frequency response. So, let us frequency domain. So, we will wait until that. So, get a feel for what it is. So, if that is the case, right, if you break the signal f of x comma y into its frequency components, so you could calculate what is this called as your magnitude response, or your magnitude spectra, right. This is your real part, this is your imaginary part, right. So, this is your magnitude spectra. If you do a square of this, then it becomes power spectra. So, here we are just doing magnitude spectra, and this is your phase. So, you can decompose into magnitude spectra and phase spectra. Notice you have to need both of them to uniquely identify f of x comma y. Clear? So, let us now use this to run through some basic properties, because we see this transform is very powerful. So, let us see what are the good properties of this Fourier transform that will make us play with this little more comfortably. Okay. So, before we jump into that, just one slide to give you the big picture of what do we mean by frequency components and how to visualize, right. So, what do you see in the first row it says signal, just because we have covered signals, right. So, what is this signal? Oh, it has 2 dimensions, x and y. Remember, we are not plotting this, we are visualizing this 2-dimensional signal as an image. Okay, so that is a concept that we brushed. Then you can see a head, right, I mean, but then which direction of the head is this? Side views or sagittal. So, right. So, you should be able to appreciate the view, you should be appreciate what this 2-dimensional signal representation is. It is in the form of a image pixel. Each of the pixel value has a different shade, right, black to white, depending on the value that it contains. So, that is your image. So, now what do you see here? This is going to be your magnitude spectrum. What does that mean? That means I have taken the Fourier transform, I have decomposed this 2D signal f of x comma y into capital F of u comma v. So, we are obtaining, so this is your u and v, the 2 directions, the frequency in along x axis and frequency along y axis. Clearly you see one thing, I mean, for most of you, if you look at this, you cannot really make out anything. I mean, this you can really, spatial domain, this looks like a head and we know what it is, right. So, this is head, inside there is some brain part, and this is nose, this is mouth. I mean, we can, we know what it is, whereas here it is very difficult to interpret. However, there are some salient points, salient aspects about this that we can still intuitively interpret. Okay, that is the goal of this slide right here. So, first things first. Okay, so this is the signal and it contains all of these frequencies, meaning all of these frequencies are contributing to getting this image, right. So, what is this frequency? Oh, we know, we saw from the visualization, remember, go back to the review of signals when we talked about how to visualize the frequencies. What do we mean by spatial frequency u and v, right? We had that parallel bars that are running black and white horizontal vertical pattern, and then that was at an angle. So, we calculated u frequency and v frequency. What was that? Oh, what do we mean by u frequency? That means how do you have a fluctuation? What is a fluctuation or oscillation in this case? Black to white or white to black, or the pattern. So, that is your variation, the intensity variation along your x axis. Likewise, your intensity variation along y axis, intensity as in the cyclic variation, right, black to white to black. Remember how we plotted that. So, essentially number of cycles of that is there is going in the y direction is going to be your v frequency. So, if you look at it clearly, you can see here, if I draw, there is going to be white, black. So, there is a y component, there is a frequency in the y component, there is a frequency in the x component, right, u direction. So, wherever you see vertical lines, right, or featured here, that means it is going to have variation in the horizontal direction or the x direction. So, there is going to be a u frequency. So, clearly you can see that means in this space you have several frequencies. Okay. So, it need not be just u and v that is perpendicular, it can be at any angle. So, here for example, I mean this goes from horizontal to vertical. So, you see so many angles. So, it is all perpendicular there. So, the frequencies along, there is some frequency in the u direction, some frequency in the v direction, right. So, some other point u comma v. So, remember when we also saw an example of u and v both being non-zero, right. So, that means you have both the frequencies. So, that is how this plane is populated. So, how do we appreciate? Okay, even though here it is very difficult to appreciate any pattern, we can still observe few things. One is there is a bright spot at the center, right, and probably it gets less denser as you go outwards, that is higher frequency. So, this is your frequency axis, center is 0 comma 0, 0 comma 0 is the center. So, this is your u, this is your v, right. So, there is positive frequency, negative frequency, up and down, 0 comma 0 is at the center. So, clearly what you see is, if for example we remove, right, frequencies that are above a certain frequency. So, this is blackened out, right. So, that means the high frequencies are removed. When you remove the high frequency in the frequency content, how does the image look? Wow, it looks blurred, right. More physically, if you want to appreciate, the edges are now looking less prominent. So, for example, you still see the shape of the head, you still see the brain, right, you see the structures, but then it is not sharp, right. Look at here and look at here, it is not sharp, the transitions are not as sharp as in this image. So, that means there is no rapid transition, rapid transitions are minimized. What do we mean by rapid transitions? That means the fluctuation from white to black to white, right, that is becoming less prominent, that means it is slowing down. That means the high frequencies, if it is transitions are fast, that means that is high frequency. So, if you remove the high frequency, the transitions become less visible. To extreme cases, if you really cut down, right, then you notice still you are able to see that this is a head, this is a nose, more or less you are able to see the structure, but it looks more or less homogeneously white. You really do not see much transitions. You have some transitions which are captured, but predominantly what this says is all of the energy is, if it is contained only at the center, that is your DC value or zero frequency. If there is zero frequency, what is the meaning? There is no oscillation, meaning there is no change, there is no fluctuation in the intensity. That means if this is only one value, right, if there is high contribution from 0 value 0 comma 0, there is no frequency, this should look flat, this should look same value throughout, which is pretty much what it is. Of course, you have some frequencies still left and therefore you see subtle. So, if I go ahead and filter it further and use only this frequency, this will become like a disc, right, white disc. That means you just have one black to white transition, another white to black transition within this whole space, whatever this length scale is. So, you have one fluctuation per length, right, you see, or nose fluctuation per length will become 0 value, right, that will be your only one point. So, if you have only one point, one frequency at 0 comma 0, which is your DC frequency, and that contains all the energy, that means your spatial is going to be flat, equal to 1 everywhere, right, that is what you expect. So, the main point that I would like for you to appreciate here is, so looking at this image, physical dimensions, the length dimensions in the spatial domain, you can now perhaps eyeball and appreciate what do we mean by spatial frequencies. Okay, in time domain maybe we are trained, you could look at a signal form, the wave form, and start to count how many cycles are there and you can guess the frequency. So, here as well you should be able to visualize what it is, even though the 2D spectrum is going to be not really having much pattern, right, it is going to be have a DC and then high frequency content. The pattern will be visible here. Okay. Good. So, we now know what is frequency, the Fourier transform, and how do you get from spatial domain to frequency domain. And now let us move on to look at some of the properties. Okay, so the way we would like to do is, since this is a review, I would just list this out, that will give you few seconds to perhaps recall, connect with what the property name would be. All of these that we are going to cover should not be the first time that you are looking at this or hearing about this. If that is the case, then I sincerely recommend you go back and review, right, read one dimension first and then look at this. Okay. So, what is this? In fact, some of this that we will cover, we just reviewed for systems. Okay. Anyway, so what is this? This says, this is the Fourier transform operator. So, this is your f of a1, f, that is I have a function small f, I have a function small g, f of x comma y, g of x comma y, a1 of f of x comma y plus a2 of g of x comma y. If I send them through Fourier transform, right, if I take the Fourier transform of sum of these two signals, right, weighted by a1 and a2 respectively, that is equal to a1 f of u comma v, that is your Fourier transform of f of x comma v is f of u comma v. Fourier transform of g of x comma y is g of u comma v. So, does this ring a bell? When I give input as weighted sum of two functions, the output of that is output of the individual ones through that system with the corresponding sum of respective outputs weighted by the corresponding coefficients. What is it? Linearity. Okay. So, this again is going to be very handy. So, the idea is when we did impulse function, time domain, we use this linearity property very much, right. So, you will see that means Fourier transform also obeys this linearity. So, analysis of a system using the equivalent frequency representation of the signal will be very tractable as well. So, next, so if I have similarly, if I have f of x comma y, the Fourier transform is capital F of u comma y. So, if I send, right, if f of x comma y, if I shift the signal, so f of x minus x naught, y minus y naught, which is shifted signal, if I shift in spatial domain by x naught and y naught in their respective axes, then what do I see? What do I get? Oh, if I take the Fourier transform, right, this is the magnitude. So, your magnitude of f of f naught, x naught, y naught, just to represent this, u comma v is nothing but f of u comma v, fine. More importantly, there is e power minus j 2 pi x naught y naught. That means, if I shift the signal, the magnitude of the Fourier transform does not change. Okay. The magnitude of the Fourier transform of the shifted signal does not change, it is still f of u comma v. But what changes? It reflects in the phase shift, or right, your frequency here, right, u of, so your exponential. So, there you have a shift. So, that is your phase shift. Remember, we talked about magnitude plot and phase, magnitude spectra and phase spectra. So, magnitude does not change. So, if I shift the signal in spatial domain, the magnitude of the Fourier transform remains same, only the phase shift. So, this folds as a phase shift, very similar to in one dimension if you do time delay, right, at least that is that usually if you do time delay, you will have phase shift, similar thing, right. So, nothing much to that. So, these will be very helpful in playing with this thing. So, this is your translation property. So, if you translate in space, it will have a phase shift, magnitude will not change in the Fourier domain. Okay. So, then properties of conjugation and conjugate symmetry. So, if you have a complex, if you have if capital F of u comma v, right, is the frequency Fourier transform of a complex signal f of x comma y, for example, right, then the Fourier transform of f asterisk. So, this is your complex conjugate, this asterisk of u comma v is f complex conjugate of minus u comma minus v. So, this is your conjugation property. Likewise, if you f of x comma y is a real valued, right, and f of u comma v is the Fourier transform of that, then you have f of u comma v will be equal to f asterisk complex conjugate of minus u comma minus v. So, this is your conjugate symmetry property. So, all this even function, odd function, right, conjugate, real part, imaginary part, what is the phases symmetry, magnitude is all this very similar to your 1D equivalent, nothing new here. So, it might help for you to brush that up. Okay, so far it is just direct extension of what we know in 1D. This is another thing, right. If you have what is this representation, it basically says the small f is your spatial domain signal, right. So, in the spatial domain f of x comma y, if a and b are the respective values of scaling. So, f ax, f then by. So, that is what this a b denotes. So, if you have f of x comma y and the Fourier transform is capital F of u comma y, if I now have an input signal which is scaled f ax comma by, right, what will be the Fourier transform of that? Fourier transform of that will be f of a comma b u of e equal to, see the inverse, right. So, this is your scaling property. Okay, so you can, similar to what we covered, you could see what happens if a equal to b equal to minus 1, right. So, it will become f of minus x comma minus y equal to capital F of, right, Fourier transform will be capital F of minus u comma minus v. That is, if you reverse your x and y, your Fourier transform also gets reversed. Okay. So, this is your scaling property, very similar, nothing new here. Okay. That is fine. This is something that is interesting. Again, now that we are going to 2 dimensions, right, in 1 dimension this is you can probably have only symmetry around the axis, right, whereas now what do you see here, this is my f of x comma y, regular f of x comma y, I have added a theta here. So, what does this mean? If I have f of x comma y, that is my signal, f theta of x comma y represents a signal which says it is a rotated version of f of x comma y, right. So, f of x comma y, if it is there, your Fourier transform is capital F of u comma v. Now, if I represent f theta of x comma y, which represents a signal f of x comma y that is rotated about the origin by theta, right, f of x cos theta minus y sin theta comma x sin theta plus y cos theta. So, it is making some angle, so it is rotating by theta degree. Then what happens to the Fourier or this frequency spectrum representation of this signal? If you rotate in spatial domain, what do you think is going to happen in the frequency domain? Well, very interesting. Very nicely, if you rotate it here in this direction in your spatial domain, it is equivalent to rotating your frequency domain. So, if you f of this function, right, f of rotated version. So, you have a Fourier spectra when it is capital F of u comma v, when the signal is f of x comma y. If you rotate the signal, right, at angle theta, f of x comma y is rotated by theta, then the original spectra capital F of u comma y is also rotated by the same amount of theta. So, essentially if you do the space, it makes some sense, right. If you intuitively look at the examples that we covered, there was a horizontal pattern, black and white stripes were horizontal pattern. If I now, so when we did that, what did we say? Oh, we said the frequency is changing only in u direction, it is constant in v direction. So, v was equal to 0 and u had some frequency, I think 1 or 4, the 1, 2 and 4 is what we covered, right. So, imagine instead of vertical line, you rotate that, what will happen? It become a horizontal line. So, now your frequency domain, whatever was there in the u will become to v, v will become to u, right. You are rotating the frequency. So, you will have u equal to 0, right, the frequency along y direction, if you go turn it, right, whatever was parallel vertical, if you turn it to horizontal, now you will have variation only in the y direction. and it will be same in the x direction. So, your u will become 0, we will have those frequencies. So, it will look like you are shifting or you are turning, rotating the frequency domain. Okay. So, this is called as your rotation property. So, these are all very interesting and important, because you will encounter, because we talk about 2 dimension, if it is going to be rotation, right, we talked about, without jumping into detail, to just appreciate why you might encounter this, we talked about views, different views, remember, projection, different views. So, you can already start to imagine you will encounter rotation quite frequently. Okay. Is there anything else we want to do here? Last but not the least, very powerful, right? What does this say? When you do convolution, so it is very similar to your time domain. When you do time domain convolution in the time domain, same effect is obtained when you do multiplication of their respective frequency domain, right, in the frequency domain. So, similarly here, so whatever, if you do convolution operator in spatial domain, you can get the same effect by doing multiplication or product, taking the product. So, if you have 2 signals and you convolve, you get an output. So, instead of doing convolution in spatial domain, what I can do is take the Fourier transform of the first signal, take the Fourier transform of the second signal, and then multiply them. I will get same effect, right, operation on the signal. So, the net output signal will be the equivalent. So, this is again a very powerful, whether you want to implement your algorithms in time domain or here in this case spatial domain or in the frequency domain. So, this back and forth you will have to do several times. Okay. So, this is a very interesting property. Likewise, if you have multiplication, right, if you have 2 signals which are multiplied in spatial domain, then you could take their respective Fourier transforms and do a convolution in the frequency domain. You will get the same output signal by these operations. Okay. So, that is something that is very powerful. You will encounter that at least at the time of implementation, when you are implementing certain algorithms, when you are doing these operators, whether do you want to use frequency domain operators or time domain operators, spatial domain operators, which is efficient, which is accurate, all these things you will encounter. Okay. So, just to state another useful one is, like I said, for systems also, right. If you have capital F of u comma v as the 2D Fourier transform of signal small f of x comma y, right, that is fine, you do the Fourier transform operator. But instead of doing the 2-dimensional Fourier transform, you can also do 2 1-dimensional Fourier transform, meaning you can take the Fourier transform along the x direction and then cascade it with do Fourier transform again on the y direction. So, you can accomplish the 2 dimensions, you can separate the 2 dimension as 2 1 dimension. That is what we mean by separability, and this again will be used just for simplicity, right. Instead of accomplishing 2 dimensions, you can do it as 2 1-dimensional operators. So, you can separate the 2-dimensional Fourier transform into 2 1-dimensional Fourier transforms. Okay, this is what I was waiting to get after. Transfer function. All the other properties are fine, but this is a very important one. Why is this important one? The name is same, transfer function, you would have heard. What do you mean by transfer function from your previous prerequisites? Oh, that means it is transferring, this transfer function transfers something from input to the output. Isn't it what we talked about system also? The system H transfers the input, or operates on the input to get the output. Here it is just a Fourier transform. So, you can say transfer function, it transfers something from input to output. What is that it is transferring? It is transferring the frequency content, right. So, essentially transfer function is an important concept. We saw the system impulse right, a function for a response in the spatial domain. So, if you are going to do spatial domain analysis of the system, right, you do all that, you can use the impulse response. Whereas, if I want to do the analysis in the equivalent domain of the frequency, then I need something to analyze it. I need to be able to characterize the system in that domain, right. So, the H we were able to characterize in the spatial domain. If I know if I present the impulse response, the system's output is considered as the system impulse response or system point spread function, specifically for the 2 dimensions, right. So, that can be used to analyze the system in spatial domain. So, if I want to do that in the frequency domain, then we need to characterize the system in the frequency domain. So, how do we do that? Think about how we did in the spatial domain, same equivalent we should do. There what did we presented the system, right, with a impulse, right, a impulse we presented it, and whatever came out we said, oh, that is how it responds to that impulse, and therefore any arbitrary signal can be viewed as collection of shifted impulse with that function, and therefore we used all the linear spatial invariation, LSI, right, shift invariance. That is what we did. So, here likewise, how do I decompose the signal? There we were able to do f of x comma y was, we used the impulse shift and we got different locations. How did we do here? Oh, when we talked about frequency response, we talked about there should be a basis, there should be a frequency that we should apply, right. So, if I now give a system into the system instead of an impulse, right, I need an impulse in the frequency domain. What will be an impulse in the frequency domain? A sinusoid, a particular frequency, or a cosinusoid, a particular frequency, right. Any oscillations with one particular frequency will have frequency representation, will have only one point, it will be existent only at that frequency, right. So, if I present the system, right, if I present the system with a typical sinusoid or cosine, so we will write it as a complex exponential, right. So, if I hit the system with a complex exponential, right, we were calling this as f of x comma y, f of, right, remember, and h of, and then your double integral, we got the output. That is how we wrote when we talked about spatial impulse. That time we called the signal as f of x comma y to be generic. That input signal is now complex exponential. Why did we pick complex exponential? Oh, because we know this is sinusoid or cosinusoid with some frequency, specific frequency u and v. So, this is our just substitution, right, we put this. So, from now we need to do some simplification to understand what this can be viewed as. Okay. Quickly looking at this, nothing is obvious, just we can recognize that, oh, we did not do anything fancy so far. Instead of what we used to do f of x comma y, we have replaced that f of x comma y, the input signal, with complex exponential. That is all we have done, and this is your system impulse response, right. So, this is your system. So, input system, this is your output. So, nothing fancy. So, now what we will do is, we will do some maneuvering and I will show the result here, but what you can start to think is, okay, we can do some change of variables, right. I can look at this and say, look, x minus epsilon, I have a epsilon here, right. So, maybe I can do a change of variable. So, I can do u of this epsilon, I can write it as here, just do variable substitution. So, the idea would be, I can break this exponential right here, right. If I break these two, epsilon eta, x minus epsilon, y minus eta. So, I will do change of variables, so that this, whatever you have subtraction here will go there, Why is that important for us? Oh, if exponential, if you have 4 variables plus minus, you can basically, it's easy to split, right? Exponential dot exponential, you will have, you can split it multiple exponentials, that is the logic. So, we will just do some change of variables. I would let you to work here, do the change of variable, and you will quickly realize it is just one step wonder. If you do the change of variables and rewrite, right, you can get to this form of g of x comma y as h of u comma v times e power e of j 2 pi into ux plus vy. What is this h of u comma v? H of u comma v is nothing the Fourier transform of h of this guy. Okay. So, this is not that, so you can actually look at it how we, one step in between that I missed. You should be able to eyeball and convince yourself that yes. So, if I have this, I can change this to epsilon and eta. I am just going to use the same variables, just dummy variables, right. So, I will change this to epsilon and eta. So, that is how you get this, and this will happen x minus epsilon and x y minus eta, right. So, then I can obviously group x and y, right, together, and eta and epsilon together. Okay. So, there should be a negative here, right. If you do that, x minus eta, so there will be a negative here. So, if you do that, you can quickly recognize this term times this term in this double integral form. You can recognize it as h of u comma v. Of course, the variables are only eta and epsilon. So, you will have here 2 pi ux vy, right, that will just come out because that is not the running variable here. Okay. So, just substitute variable and you will quickly be able to group the terms, or at least look at the grouping and identify that the double integral of h of epsilon eta, right, e power minus j 2 pi this guy is nothing but the Fourier transform of h. What is h? System function. So, essentially h, capital H of u comma v is the frequency response of your impulse function or your system function, which we call as the transfer function. Why is that? Because it is transferring the frequency content from input to output. Okay. So, I would let you do this one step in between and convince that you are able to get the frequency response, or the you can spot the h of u comma v. Okay. So, of course, there are several important properties, but like I said, this is only for quick review that we are interested in. So, one of the other important property is we talked about circular symmetry, right. We talked about this f theta of x comma y is nothing but, if you have f of x comma y and you have f theta of x comma y is the same f of x comma y that is rotated, right. So, if this is the case, f theta of x comma y is equal to f of x comma y, that means it is circularly symmetric. No matter which angle you look at, the function looks same. So, whatever you have f of x comma y, it does not matter which angle you are looking at, right, then it is circularly symmetric. Whether you look at it at 90 degrees, 0 degrees, it does not matter, right, the f of x y is same. So, it is f theta of x comma y, if it is same. So, any same as your f of x comma y at for any theta. So, that is your spatial domain signal. if that is the spatial domain signal, which we call as circularly symmetric, then our interest is in the Fourier transform. How does the Fourier transform of such a signal look, right? How will it look? Oh, that will also be circularly symmetric about the origin. I mean, roughly, just so that you get comfortable, you are able to position the concept in 2D when we do 1D, right? If you have a Gaussian shaped time domain signal, what will be your frequency spectra, the shape of the frequency spectra, that will also be Gaussian, right? That is something that you know. So, similarly here, if my spatial domain is circularly symmetric, because we have one more dimension, circularly symmetric. So, imagine you have a bell, right? You have a bell, that means your frequency response, right, that is also going to look like a bell. That is what this physics, I mean that is how you intuitively get a feel for what this circularly symmetric means. That much is straightforward, not a big deal. But then we will have to look at little more detail as to how do we compute this 2-dimensional Fourier transform. So, if I have f of x comma y as circularly symmetric, that is f theta of x comma y, that is the input signal, special case where the input signal is circularly symmetric. It turns out the Fourier transform is also circularly symmetric. So, we can write instead of 2 dimensions, if such a case, instead of 2 dimensions, write r comma theta. If theta is same, right, irrespective of theta, the signal is same, then we can reduce the 2 dimensions into 1 dimension. So, you can essentially try to write f of x comma y as f of r, only a function of radius, right. R is equal to square root of x, because it is theta, it is circularly symmetric, it does not matter. Okay. So, if this is, so we said if this is the case, the Fourier transform is also symmetric, circularly symmetric, therefore, we should have a equivalent there. So, your f of u comma v is also going to be symmetric, and therefore, there also we could write it in terms of only one parameter, which is your radius parameter in the frequency domain. So, you can get your small q as square root of u square plus u and v are your spatial frequencies, right, u comma v, your spectra axis are u and v, horizontal fluctuations in the x direction and frequency in the y direction. So much is good, it is straightforward, right. Okay, I see the benefit of having a circularly symmetric case, because if the signal is circularly symmetric, the Fourier transform is also circularly symmetric. If it is circularly symmetric, the 2-dimensional 2 variables, I can reduce it to 1 variable, and therefore, I can get 1-dimensional f of r is 1-dimensional, f of q is 1-dimensional. But pretty much what is not said here, what is not taken for granted, what you should not get confused, we have not really related f of r and capital F of q. We know the 2 dimensions are related, right. The 2 dimensions of f of x comma y and capital F of u comma v are related by Fourier transform. But what about when you reduce the variable, because it is circularly symmetric, you get f of r 1 dimension, capital F of q 1 dimension. Is there a relationship between these two, right? Of course, it is there, mathematically there is, but it is not what you think, it is not same. F of q is not Fourier transform of f of r, okay. Instead, f of q is, you have 2 pi 0 to infinity of f of r. Remember, in Fourier transform, we had complex exponentials, right. The signal was multiplied with e power minus j, but here what do you see? The variable, this is dr, but what do you see? J naught 2 pi with an argument of 2 pi q r. So, this is nothing but a 0th order Bessel function of first kind, okay. What is, so this is a unique function, so we can arrive at that by considering your Bessel function of the nth order of first kind is having this relationship, right. So, if this is the Bessel function, then what do we want? Oh, we want 0th order. So, if this is for n, then we can substitute 0, right. We could get J naught of r is equal to 0 to pi of cos of r sin phi d phi. Okay. So, this is called as your Hankel transform that relates your in a circularly symmetric case, right, of if the signal is circularly symmetric, the Hankel transform relates the spatial domain and the frequency domain. The one dimensional, right, equivalent is related to what is called as Hankel transform. Why is this important? I mean, if you want to calculate the two dimensional frequency response, you could calculate it through in this case of circularly symmetric, then you could actually calculate the Hankel transform and then arrive at your 2D Fourier transform. Okay. So, this is forward Hankel transform, this is going to be your inverse Hankel transform. Okay. So, I think this probably is more for most of you, these two, this Hankel transform and the relationship with circular symmetry might be new first time, but it is very intuitive. You do not, of course, these might seem little scary, but if you really look at it, this is not circularly symmetric, right. Is this a weird condition? No, actually if you look at it, a patient, the system, right, the imaging system, the patient goes in, right, no matter how you orient yourself, the output should also come out correctly. My head, if I go in particular direction, I get the head. If I go in another direction, that should also be rotated. So, circularly, so most of the time, if that is rotation invariance is expected, which is what will happen, then your system response, right, your system function, your PSF or point spread function or your impulse, point impulse response to that, that will be circularly symmetric as well. So, this is something that you will encounter. Okay. I think this is a good point to stop our review of signals and systems. From the next lecture, we will jump into some basic concepts behind how do we talk about, quantify, understand and what do we mean by image quality, because at the end of this we are going to use all these measures, metrics to communicate what a image quality is and how do we characterize the image by its image quality and how do we relate the parameters from physics, from the instrumentation, from the image signal processing, how does it affect the end image quality. Okay. So, for now let us stop here. I will see you next time in the review of image quality parameters. Thank you.